I'd like to welcome everyone here today, no matter where you happen to be in the world. We have a tremendous number of people participating in this event. It is the largest after 9 years of doing virtual workshops in education. This is the largest event that we've had under the project called Blue Waters. We have not only the 22 sites, but there are people from 39 different states participating, from 19 different countries and 4 continents. So that's a great testament to the people who have organized this event, and obviously to the people that will be sharing their expertise and knowledge with the event. I'd particularly like to thank our fellow sponsors for this event. Argonne National Laboratory, Lawrence Berkeley National Laboratory and the NERSC project there, Oak Ridge National Laboratory, the 3 DOE participants, the Texas Advanced Computation Center, TAC, Pittsburgh Supercomputing Center, SciNet at the University of Toronto, and of course the Blue Waters project here at NCSA. They've all come together to present or to make this event possible. So I hope that you'll have a wonderful time learning about a variety of different things. This is a exciting time period to be learning about high-performance computing, supercomputing, as well as data, big data, whatever the terms you like to use, artificial intelligence, and this event will touch on all of those. So with that being said, and I'd particularly like to thank Scott Lathrop for leading this effort to organize things, and Maxim Belkin here at NCSA for helping organize everything for this event and actually coming up with some of the ideas for it. The next thing I'd like to do is, it's my privilege and honor to introduce our first speaker of the day, the keynote speaker. It's an amazing event to be able to listen to Gordon Bell, who's a premier, world-renowned high-performance computer scientist. His career you can read on many different websites and whatever. I first benefited from Gordon's activities back on one of my first jobs in computers, where I used PDP deck equipment that he had a hand in actually architecting and creating. But I think it's extremely appropriate that Gordon is speaking at this event for a couple reasons I'll tell you in a minute. Just to highlight a few things that are, I think, phenomenal about Gordon is not only his technical accomplishments, going back to multi-computers, scalable computing, and everything that you can read about. He's published 8 books. One is entitled Computer Engineering, which is still on my bookshelf upstairs. He has published many papers and many other types of documentation and presentations of his thoughts, predictions, and experiences. But he has also been involved with a number of different types of activities around computing. Obviously, as an inventor, entrepreneur, creator of technologies that we use, but also at universities as an academic, as a researcher across many different areas of computing. He instituted the Gordon Bell Prize, which many of you may have heard of. This is a long-running prize for essentially the best applications in high-performance computing. It emphasized, and it's important, and maybe even more important now, to emphasize the ability to have sustained performance, or actually true accomplishments, rather than peak performance or just theoretical performance. And the prize that he funded does that every year at the supercomputing conferences. He also helped the entire nation in terms of establishing computer science funding when he was at NSF. He led the effort to define the NRAN, which is one of our national backbone networks, in addition to the computing activities. Gordon has spent his many years documenting the experiences and history of computing. He founded the first computer museum. I was fortunate to be able to go see that when it was in Marlboro, one of the Marlboro buildings that Digital had, and then has evolved into the computer museum in Boston and the one in Silicon Valley, where he's on the board of those organizations. But he also is dedicated to documenting his life and his activities with a digital presence, a project called My Life, where for many years he has been documenting his activities with personal wearable video devices, digitizing everything that he's done. And it's an amazing collection of things if you go look at any of his websites for that. And that's part of his work at Microsoft Research to be the subject or the guinea pig for such a robust project of basically recording all aspects of your life in an open way. And maybe he'll talk a little bit about that. But the reason I think that it's most appropriate to have Gordon talk to kick off this event is that he has spent a career in scalable, high performance, and big data applications, computing, and architectures. But he also has been for a long time an advocate and a researcher and developer for telepresence, which is basically the art of being there without really being there. And that's what this event is all about. Spreading across the nation, 22 sites, number of countries, almost 20 countries. It's really about how can we share, how can we learn, and how can we share our activities without really being there physically. So I think it's a great synergy that Gordon will be able to bring in discussing the topics for today. So with that, I'd like to turn it over to Gordon.
Okay, good afternoon. Thank you, everybody, today for joining us for another presentation by Gordon Bell. So I'm going to give a very brief introduction. You don't want to hear too much from me. I'm sure you're much more excited to hear Gordon's presentation. A little bit of background. So most of you are probably familiar with the Gordon Bell Prize that's been awarded at Supercomputing Conference since 1987. So it recognizes outstanding work in parallel computing. Just want to mention a few things about Gordon's career. So he has degrees in electrical engineering from MIT. Has a long and distinguished career at DEC, where he was the Vice President of Engineering in charge of the VAX. He also taught at Carnegie Mellon University. He was the founding director of the SIZE Directorate at NSF, which is the source of much of the funding for what we do for the Supercomputer Center programs, TeraGrid, XSEED, and the large-scale systems that are allocated through XSEED. And it would take a long time to go through all of his awards and distinctions, but I will just mention a few of them. He is a fellow of the ACM and IEEE, and a member of the National Academy of Science and National Academy of Engineering. So with that, I'd like to turn things over to Gordon.
Thank you, Bob. And what a delight to be here with, and congratulate first the organizers, the faculty, and then most of all the almost 1,000 scholars that are located on 4 continents and 22 sites doing high performance computing. So what an impressive institute and week ahead that you're going to have learning about or worrying about high performance computing. The title, as you can see, is really posits the problem that you face as we get these wonderful new machines continue to emerge. And it turns out that we're in an era where the challenge is really how do you make use of all of the power that they offer. I'd say we will all be surprised going ahead in these next years. If you start from the very beginning, we can look at, say, what an easy time it was from the beginning of really scientific computing starting, well, I'll say with Fortran in 1957, and then there was sort of almost 40 years, unbroken years of easy programming. That is, Fortran said it all, single memory, single instruction stream, and a nice way to posit your data structures and arrays, and so on. Now we're in it, and if that was low-hanging fruit, we're now going into the high-priced, high-placed fruit area where they have to be attacked with ladders and aerodromes and so on. So the performance over much of this period has really been a gain of 1,000 every decade. Now, interestingly, if you think it takes 10,000 hours to master something, and you get a new computer every 10 years, then every 5 years you master that computer, and just as it be, and then you've got 5 years of productivity. And all of that comes about from forms of parallelism, algorithms, and new specs. Another way of looking at computing is that there's been these shifts in paradigm, that the different things that you, in a sense, things that you can do or different attacks with science. And if you start with one we'll call, where the first one was really named by Ken Wilson, a third paradigm, and I'll describe what the first and second remind you later on, but was Ken Wilson, a Nobel Prize winner in 1987 or so, said it was the computation or simulation was the third paradigm of science. My friend Jim Gray, who's a database, one of the founders of the database, in 2007, said that we'd entered the fourth paradigm based on data science databases. And now we're talking about potentially a fifth paradigm based on AI. All of this allows you to attack new problems and do new science, new engineering, and new developments that come from all of these surprises. So all of you scholars, who are entering the field, you are interested, and you are entering an era of a great ride. I'm going to start by talking a little bit about hardware, namely Moore's law, that sort of what sort of forms the basis of what the computers do, and then how that, and contrast that with algorithms, and then talk about this idea of capability versus capacity computing. And so when we talk about capability computing, as we put these very large computers together, it's those programs that use all of those computers at once to solve a single problem. And that's an interesting, I'll have an interesting example that I like to use there. We'll regurge again on the paradigms, and to touch on this petascale program that's being run today that recognizes the fact that with the exascale computers, then we're stuck with having to have totally new software, and the petascale program is aimed at being able to make sure that those will all work. Now in here, these four, I'll say these are the kind of four horsemen of parallelism, and the different forms that you will encounter during this the Petascale Institute. The first being that what I'll call job stream or ensemble parallelism. That if you're given 1,000 computers or 10,000 computers or however many that you're given, then ensemble, the easiest way is you simply give everybody their own computer, and that's massively parallel, but it's also embarrassingly parallel. Never overlook embarrassing parallel as the way to get work done. And particularly, I think as you write all of your programs, almost start with the core that assume that you can have any number of computers, and so figure out how, if you have those computers allocated, how you're able to get your work done more rapidly and more easily. The second form of parallelism that we've learned to deal with is having a single shared memory and then a lot of processor, a lot being about a dozen or so processors that access that memory in parallel. And it turns out that's nice because usually the compilers will exploit that for you and take you through that and mask all the pitfalls that parallel computing gets you into. Now the third one coming down now parallel, given that you have all of these computers now versus a single memory computer, we have massively parallel coming in, and then by having those computers separated, we now have to do concurrent sequential processing. So you have all of these computers, and the thing that ties those together is a message passing interface. So that as you compute in each one of those, then you have to send data among those machines. And then the final one is, I think, is probably the most difficult of all, and that's you have a single computer, single instruction, and then you're controlling lots of processing elements at the same time. Now, ironically, that came from the gaming industry. That came in from computer games and GPU or graphics processing units, where you clearly had to do things in parallel to make pretty pictures of these scenes and games where everybody's killing one another. So we're going to look at through that. I want to start with something about my favorite probably computation and most impressive computation that we have, and that has to do with climate and climate modeling, and that many of you, I hope, are following. But I recall in looking at having a presentation of that, and probably a little over 20 years ago, when the people at NCAR described that they now could, in fact, pin the effect of the difference in those curves, that lower curve being what climate would like to do, and then the upper curve, which is what climate is, and describing the reason is that difference really had to do with man-made effects in the atmosphere. So I'll say without supercomputing or without high performance with computing, we would still be arguing about whether man-made activities affect climate. Could you believe it? Now, I love this little graph that was, or this little photo of a computer that was never been built, but a scientist in the UK, in fact, said this was 100 years ago, conjured up a computing factory where all of the people sat around in this amphitheater or this theater and did computations and simultaneously were able to transmit data or transfer data to their neighbors and to the different rows and columns as a way of doing sort of the finite element kinds of computing that climate conjures up. The other thing was, for example, at Illinois, has worked a lot on hurricanes, and only recently have actually said, well, things are really worse than we thought because we're able to take the effects of CO2 mixing in the ocean to show how that affects things more. So we're continuing to learn more about and describe better the effects of climate, man-made climate effects on. And then finally, in the UK, the medium range weather forecasting, they have claimed this is really the wonderful application for exascale computing. So those are kind of the basic from a weather point, from a climate point of view. Now I'm going to turn to probably the only slide on, mostly the only slide that has to do with hardware, and this is kind of the one basic slide that tells everything, and you'll be able to read what all those 5 curves are. I'm only going to concentrate on the brown one in the middle, and that is the clock speed of microprocessors, or the clock speed of logic, and that now, unfortunately, you can see that's been a constant for about almost 20 years, and that constant is somewhere between 2 and 3 gigahertz, or 2 and 3 billion operations per second. So when you put hardware together, you put it on a chip, then the operations internal to that chip are being result from a clock of only 2 to 3 billion operations. So we're stuck with the clock speed. So in fact, there's really no magic bullets for exascale like we've had in the past. So with an operation rate is 2 to 3 gigahertz, and we're trying to get to exa being 10 to the 18th, and we can only do 2 times 10 to the 9th, then we're stuck with another half billion operations that half billion full parallelism that has to occur. So therein lies the terrible dilemma and the difficulty and the challenge for all you scholars as we move forward into what amounts to different forms of parallel computing. So typically you may have 100 to 10,000 independent computing elements what we think of as computing elements, such as the ones you have on your right there on your desktop. It turns out in this case, each of these elements, these computers, actually cost about $50,000. Because if you put them all, look at what we've just we're focusing on today, there have been about 3 contracts let for computers developed in 2021, 22, 23, and they're all about $500 million. And they all have about maximum about 10 of these independent computers that have to work together. And then if you look inside that, then there's, of course, multiple processors and things like GPUs to have multiple processing elements within those processors. And then you may actually have hardware that you use to unfold things like the FPGA gate arrays to get those operations up. And then finally, if you want more operations, the other thing you can do is make the operations not quite as big, and then if you only have 8-bit operations, the way that you can have a lot more of them than if you're doing 128-bit floating point arithmetic. This a curve of one of the amount of parallelism. You'll see that you can relate that back to that first graph with all of the curves. But this is the number of independent processing elements in a single computer, and you're seeing that ends up either within graphics processing units or the modified machines today of approaching about 100 under control of a kind of a single instruction. If you look at from a software point of view, it turns out that Jack Dongarra has plotted the performance gains from algorithms that are used in the LinPack and the linear algebra packages that are used for dense matrix operations. And these, by the way, have exceeded Moore's law in terms of performance. So now it's software that's a matter of where we expect to get the gain. And then the same thing is true for many of the many algorithms or many applications you run for example, for combustion simulation and for MHD, or these are magnetic energy, fusion energy calculations for magnet or hydrodynamic simulations. It too is improved faster than Moore's law. So it's now a question of algorithms for speed. Now I'm going to take a trip through some of the computing of the supercomputers, because I just happen to love visiting computing centers. Before that, let me comment about, well, what is the ideal supercomputer? You had your others. Well, first you'd like to have the clock go on and increase in operation speed forever. Second, you'd like to have a single shared memory that you can easily allocate everything into, and then particularly that then you'd like to have processors that could then come into that memory and absorb all those memory cycles of the infinite memory and infinite speed memory. Well, what's happened was, as we watched computing develop, that a number of techniques for parallelism evolved. First, just by overlapping memory and getting more memory capacity, pipelining so that you have lots of operations in flight at the same time and going through pipeline machines. And then in 1975 or so, Seymour Cray said, let's make all the operations be vector operations. And then that got us almost another factor of 100 that was pretty easily to manage. And then when you ran out of that, then you start using multiple processors to absorb that memory capacity. And then we find that Moore's law didn't hold forever for speed for various reasons. And so we're stuck with then having to go to totally independent computers to get essentially more operations per second. And with that, we've switched from a hardware-driven evolution to really a software challenge that comes with having what I call multi-computers versus mono-memory computers that we were so lucky to have live with us for such a long time. And with all of that, then again, history is being repeated as each of those memory nodes followed the same evolutionary path as the original memory, as the original computer did, the mono-memory computer did when it was evolved. So history is repeating itself at every node in these massively parallel machines. So it's really about speed that comes with parallelism, and then having standards and being able to take advantage of sort of commercial low-cost computers. I mark the way this computing history is, I'll say, the Cray era, and that's really the Seymour Cray era of when he developed design computers, and that lasted for about 30 years from 1964 to 93. There was a period of about 10 years when there was, I'll say, it was a search for parallelism. That is, how are we going to get more computing done? And there were so many attempts to do that between 1984 and 1993. And then finally, we've agreed upon what it is. And so for the last really almost over 20 years, then there's been a settled, and we're working on multi-computers, or we call them clusters, or massively parallelism. But these are independent computing units that in fact are tied together with a network switch of some kind, and then you have the challenge for all of you is to break those programs up on and run them on those independent nodes, and then and get the answers to come back kind of in the right order and having them be correct. This says it graphically. You can see beginning in the sort of 1965 or so with the first Cray, the CDC 6600 up through the last Cray multiple processor vector processor computer was the mono memory computer era, and then we entered into this other era with the overlap. And so if I look at the kind of seminal events, we're going to look at about some of these seminal events that occurred over this period, really since Fortran. The first one, of course, to me is the big event, and that was the Big Bang, which was the recipe for the computer itself, and that occurred in the late 40s. And then, in a sense, Fortran and John Backus's team at IBM that created Fortran really set the standard spec for what a scientific computer would look like, set it at an abstract level, but it was nevertheless an important one, for that was the way that all subsequent computing kind of was done. Then we had a period of people building some various early computers where the Department of Energy said they needed more. And then if I go on through that, then it turns out the beginning of the end occurred in about 1994 when it was no longer feasible to get more performance with a single memory computer. So the death of the mono memory computer occurred about that time, and it was taken over by computers that were all multiple ones. By the way, you should never pass up an opportunity to visit a computing center, and this is no exception. I love to do this, and this was probably my favorite. It was Bob who introduced me today. Introduced us to the Flash Gordon computer here at SDS San Diego Supercomputing. Now I'm there with Bob and my granddaughter, who I'm trying to convert into being a scientific computer programmer, but she's still in high school. But nevertheless, she hasn't ruled that out. And so this is the Flash Gordon computer that has a couple of petaflops, and then about 50,000 core, 50,000 computers that are are put together. I thought it was named after Gordon Moore or maybe me, but it turned out it was after Flash Gordon for flash memory, because it is a flash memory based, intensely flash memory populated computer. In 1960, it turned out that the Department of Energy came to both UNIVAC and to IBM and said, we need a lot more computing. Please kick off programs in that would be aimed at substantially more computing power. And by the way, it doesn't matter what it costs. So the idea of building the fastest computer you could ever build, independent of a price, was kind of established in the early '60s during the we'll call it the last Cold War period. This is the sort of artist view of the LARC, the UNIVAC LARC that went to Livermore, and here is actually the console of that, and from a historical point of view, that is that's Sid Fernbach there on the left, and if you know from supercomputing that's there's a Fernbach Prize that's given, and then there on the right is Edward Teller, the architect, designer of the hydrogen bomb and director of the Livermore Labs. This is kind of looking back at what's some of the cabinets in there for that computer. Now, why I'm giving this is that's the first computer supercomputer I had seen, and it was so different than any. It had rows and rows of cabinets, much like the computers of today in the high performance centers. But ironically, all of those cabinets combined had one single memory and a single instruction stream. So that's a little bit it's so small you couldn't even measure it in performance in today's cell phone terms. But in fact, when I saw it, and they opened those doors, it turned out there was about 6 inches of matted wiring in there, and those wires ran from various parts to other parts of the machine, and so I was sort of awed by the notion of supercomputers. This is the other computer that the government funded for the Department of Energy, and this is the one that went to Los Alamos. And the person there on the right is Eric Bloch. Eric is noted, should be noted for several contributions. First, he was the project engineer of the stretch, and then second, he went on to be the lead engineer and manufacturing engineer for the IBM 360 and all of the logic of those machines in 1964. And then finally, he was appointed to the National Science Foundation as the director in 1982. And then during that period, in fact, established the computing centers, particularly the ones here at San Diego and at Illinois, the first 2 national centers. And so it's really to Eric that you owe much of the existence. And I'd say without Eric doing that, it probably wouldn't have gotten done, because he was willing to fight for the budget and the needs and so on. And this is what the stretch looked like. It's bays. So essentially, I have a kind of metaphor about what you're embarking on, and that's really of mastering parallelism. So, one easy form is you simply pipeline. It's like juggling. You simply pipeline that, and then if you want a little more parallelism, you can do multi-threading. You'll notice those are different colored balls, and so you're having a couple of different jobs going in parallel in the same way. Fortran, I can't tell you how important I think Fortran was in terms of supercomputing by establishing basically a single spec that other people could use. Here's what people think of as the first supercomputer. That was in 1964, and that was the 6600 that was delivered to Livermore. And we have that at the Computer History Museum in Mountain View that you should take a look at some point. This is sort of the architecture of the 6600. On the left, you have first example of multi-threading, where you have a single processing element, and then it turns out every tenth of a microsecond, the state of the processors would get updated, and then you'd move on to the next computer. So it was multi-threaded in that a single processor was a single physical processor was managing the parallelism, managing to give you 10 independent computers. And those computers were simple computers. They were 12-bit computers, and they were used for all the I/O that went into the 6600. And then on the right is the arithmetic part of the 6600, which looks virtually identical to the modern RISC, or reduced instruction set computer, because you had essentially instructions that loaded and stored those 24 operating registers, and then you had other separate instructions that in fact specified which which computational elements such as multiply or divide or logic that was carried out. So it was a kind of a 3-address, add a couple of numbers and put them back in a third register. So that was basically how that really established the architectural structure of today's RISC computers. Now, I'll get again, you'll see me revert to sort of personal experience. At the same time, I was building a 36-bit computer for time sharing. That is a computer that multiple people could use at the same time. And to us, that was a very large machine. That was 256,000 36-bit words. Was 30 at that time, before the world settled on the 8-bit byte. There was the 36-bit. There was a 6-bit characters, and so this was one of those. That particular computer, or one like it, was used at Livermore to do memory switching, switching of the various elements in the I/O amongst the units, different elements, storage, and computational devices or computational machines at Livermore. And so I'm there with essentially the team, including, I think everybody was there except maybe 2 or 3 programmers who were still getting up or so. But that was the whole team for building the computer, including the circuit design. And what was important at that time was I got the manual for the 6600, and I said, oh my God, how in the world did anybody do that? Because I was totally in awe, having worked on a similar machine with similar logic and so on. And it turned out the secret is 6600 had about 600,000 transistors, and I think we had about 6,000 transistors. Well, it wouldn't have mattered to me at the time because my little brain didn't really have the power to understand what would I do with 600,000 transistors anyway. And so we were constrained by price and everything else. But it was awe-inspiring to see a competitive machine like the 6600 appear. And it was just as inspiring to IBM, because the president of IBM said, I failed to understand how a lab in Chippewa Falls, Minnesota, with 30 people, including the janitor, outperforms our massive engineering organization and technical prowess that IBM had at the time. So it was just as, or at least IBM had the same thought as I did when the machine was introduced. Then Cray went on to build the 7600, which was basically a pipeline, fully pipelined 6600. There was a search going on at that point still for parallelism. Gene Amdahl in '65 had said it's going to be tough, because he outlined the idea that if you attached infinitely fast processing elements to a single thread, a single processor machine, then you're really stuck by the slow part of the calculation. So he examined 3 different architectures and concluded that the advantage was substantial to have just a single processor. Since we're here in Illinois at one, Dan Slotnick at Illinois posited a single instruction multiple data machine, a very large one, 64 processing elements that would be used for highly parallel computing, and that turned out to it was operated at Illinois and then moved to NASA in '71. But by the way, what you're seeing there on the left is the processing, one of the 64 processing elements, and then on the right, that there's a 10 megabyte fixed head disk. So there were 64 of those pairs that formed the thing called the ILLIAC 4. A little bit later, Seymour Cray said, no, here's how you do it. And basically, you take all those registers that used to be scalars are now vector registers. And he built the Cray 1, having left CDC. And then he called this the world's most expensive love seat. And then on the right, I'm there on a love seat there with Steve Squires, who was the director of the DARPA's Strategic Computing Initiative, and they were aimed at building a faster computer to compete with the Japanese fifth generation that had been declared that it was going to do AI at incredibly fast rates. And of course, you just don't do Lisp at a very fast rate. You do it one memory access at a time. And then if you open up the Cray, it looks like that. These are that love seat, those love seats held these transformer bays that were the power supplies. And then the logic bays are in those at about 12 columns there, and in each one of those columns held several hundred cards where PCL logic, I think 2 to 4 gates there, and I think a half a dozen or about a 16-bit registers were. So 2 or 3. Cray used only a small number of elements there to design the Cray 1. Inside the Cray 1, basically it looks similar to the others, except it's the scalar registers are now vector registers. I won't talk about that one. That was a Cray 2 that was quite beautiful because you dunk the whole thing in flora inert. So this basically gas or this liquid, which then turned to gas as the heat of the logic there to that, and then it was cooled again with a compressor, and it was very beautiful to see this sort of kind of waterfall of liquid and liquid being boiled off and cooled again, constituted the Cray. People always wonder how does technology really evolve over time? Well, it turns out this is another Cray that two people, a person at David Shaw and Microsoft built. This is the Cray 1 of 40 years before that now is all done in a single FPGA, that is a programmable array. And so it's a tenth it's about 10 inches versus The Cray 1, I think it was a little over, about 6 feet, and then, of course, proportionally smaller. So it's roughly 1,000th the size of a Cray 1, and 40 years later has outperformed the Cray 1. So now, essentially, we're entering the era of kind of a new beginning with microprocessors. And that started really with, in 82 and 83, when Caltech, a team at Caltech, led by Charles Seitz, built an 8 microcomputer cosmic cube. That is a cube that a bunch of computers that were connected by a hypercube. Then he did the same thing for 64 elements, and that was kind of the beginning, the first computer that sort of showed you could really do very well with taking a multi-computer approach. And so that was really the beginning of this new era of the killer micro. And back in 1984, that was also the year that the NSF centers were established, and then there were a number of other events, but the key event, the ending event then, was when this period ended, finally, when a thinking machine's 100 or 1,000 node or 1,000 computer outperformed the largest Cray 1 by a factor of 4. And at that point, all the people who were worried that this could ever happen, or and we're going to have to deal with a software problem, the whole issue was settled. And I think you look at some of the important events there, but the main thing was that it ended with the spec for MPI, the message passing interface, and it ended with the Beowulf design software. And those are the things that finally culminated in this period and established a new beginning. And then now I'll follow the notion of we're doing juggling, and this is what I would say is capacity computing, that you just put a lot of processors there, and they've all got different jobs, and they're all of these objects are in the air at different times in different places. So that was how you think of capacity computing, of juggling, and in terms of capability computing, if you're trying to do those onto a single job, you have to line things up, and you're all computing really working on the same kind of work. Here's a picture of the first Caltech computer, and then the 64 computer one there at the bottom, and then that spawned Intel to be interested in building computers, and that was very instrumental in getting them building machines. Again, I'll go back to not one other personal thing that happened was that in one part that I feel responsible for these supercomputer centers was in 1982, Peter Lax created the Lax report and said, we have to have supercomputers because Digital Equipment Corporation has introduced this computer called the VAX, which is Virtual Address Extension, as the scientific computer. So scientists were buying these computers and putting them in their laboratories, and they cost about $200,000. They had virtual memory, so you were not memory limited, and but they only operated at maybe anywhere from 10 to 100 times slower than a supercomputer did. But what it meant is that you didn't use supercomputers. So I'll say I was responsible for stimulating the centers by having this computer that other people had to buy, and that kicked off the supercomputing at SAIS. And then I came to, as Bob said, I came to work for Eric Bloch and established the computing directorate. And well, that included the center here at San Diego, the NCSA at Illinois, and then a computer at Cornell and one at Pittsburgh. The other thing that was done, I'll say I made two claims there. One is you were running a Department of Energy operating system here, and I said you can't do that. You have to use Unix. And that was hard for me because we had developed the VMS operating system, but it was clear to me that the Unix standard was important. And the other thing I did was that the network is separate from the computing facility, because everybody had to worry about, all the centers were worrying about networking, and so we established the network that then went on to become the National Research and Education Network, or Internet. And then the other thing there was, other contentious thing was to the computer science community. I said, you're going to work on parallelism, and that prompted sort of outcries from Don Knuth and Ken Thompson and Richard Karp of, you mean your NSF's trying to tell us what to work on? And I said, yes. and parallelism is going to be important. I'll say I didn't succeed very much there, but we did kick that off. And then there certainly was a conflict all the time trying to establish computational science within the computers. What was the computer science director? And I'd say even today that conflict or that question still exists, and to a large degree, I don't think the two have have properly benefited from being together. And at that same time, I was at NSF, Alan Karp offered a $100 prize for parallelism of factor of 200, because people had these multiple computers that they were experimenting with. And so I said, that's a great idea. So I'll offer 3 $1,000 prizes for people who do exceptional work in parallel computing, dealing with the efficiency and the amount of parallels. And furthermore, I'll do it for 10 years. And so that really is really the origin. And every time Alan sees me, he said, gee, I should have offered more money. And I said, well, tough. Because the prize has become known, I'll say beyond my wildest dream, but what's really impressive is the work that I think the prize has stimulated, and every year I go to supercomputing and go to those 4 or 5 sessions. I just marvel at the amount of brain power that's gone to work in terms of being able to exploit these computers. By the way, and then what that did, the first one was done in 1987, and that was with Gustafson and Monterey and Benner at Sandia. They spent a whole year working on 3 problems and showed that they could get typically they could get speed ups as much as 1,000 from 1,000 computers operating together. And what they had showed really that if you had enough memory, then you could make the problem big enough to cover the overhead. And that and Gustafson did the math behind that and sort of showed that, in fact, Amdahl's law was just a barrier only for small numbers, for large amounts of sequential time, and if you make that synchronization time very small relatively, the performance is not impeded. And then again, this is the machine that convinced everybody that computing had to be in clusters or massively parallel, and this was 1,000 computers linked together, and it was the TOPS 500 number 1 machine then, and running at 60 gigaflops. And a little bit later, the message passing interface in '94 was crucial because, again, we have standards that says everybody works to this. And then the other thing that was crucial was the software and the book that said anybody can build their own supercomputer or a parallel computer or cluster. And that was a book by Tom Sterling and Don Beckett, and that was enormously powerful. During this overlap period I mentioned, 10-year overlap, about 50 companies lost their lives trying to make different forms of parallel computers. There was an era when we made parallel, small mini supercomputers. There were a bunch of those that were made, which was sort of vector. They looked like a Cray, only they were just a lot smaller and cheaper. And then, so we really are now in the cluster era, starting with the CM5, and that's sort of 93. And life has now been a sequence of building interesting machines, of going from that first machine up through petaflops and early exaflop, petaflops, and getting trying to get to exaflop computing. And then there's been a commitment of 3 contracts have been allotted for exascale computing, and those are at Argonne and Livermore and Oak Ridge. And this is one of the first teraflop machines that was at Sandia, and then subsequent machines in this one. One of the early petaflop machines that I visited. Again, you can see how I like to visit these computers. And this is a graph that sort of shows the how the Gordon Bell Prize has evolved since, in terms of parallelism, since 1987 through actually now over 30 years. So I'm so delighted that in fact it continues to evolve, particularly in a way there's no limit here, just because it's only limited by the imagination of the people doing the programming. So that's what we wanted. It's not an award for a computer, but it's an award for a computing effort. And that's where all the skill is. I met the people who were part of this effort, and this was 2017 winner, and this was a Chinese computer that had 10 million computing elements, and those inside those 40 cabinets there are 4 super nodes, and each super node has 256 computing elements, and each one of those looked like this. So the lowest level is a node that has, first off, all that. There are 4 processors that happen to have a shared memory space, and then the 2 processing elements there. One a scalar, and the other is a unit that controls 64 PEs, and so you've got 260 processors in that structure, and all operate with those in through that whole shared memory structure. So these are all now interconnected with a switch that talk to one another. So now we're in a form. When you look at the nodes, it looks more like this. Inside that node, you've got a lot going on of different forms. The other thing why this particular example is impressive is that it was a climate modeling one. And by the way, here at San Diego is Mr. Yifeng Shui, who was one of the contributors to the effort here. This is it was done in China, but basically you have these 4 coupled models working in parallel to give a complete climate simulation. So you've got the sort of ocean, you've got the atmosphere, and you've got the land, and then of course you've got a lot of ice in there, and there's a special case there. So the connecting of all these together as a model is what's kind of impressive. And then if you look at how it's actually done, and there was a team of specialists that were part of the architecture. And by the way, and if you look at the machines that are being built now, that the latest ones are this last year that achieved a peak of almost 200 petaflops, then you get a structure that is not unlike the one we just saw. Inside there, lots of processing elements of different forms. And what's happening today is those things are taking on different structure to do with building neural nets and machine learning. So as the computation changes, the architecture has been changed, or conversely, architectures are now being built to be able to exploit and give you performance in the AI paradigm. And let's just reiterating our forms of parallelism. First, simply have lots of computers and keep the jobs independently. And then if you start start to connect things, then life gets tough. And then within that, you can look, and a single memory works best, or is the simplest, because it's everything is addressable together, and then you can start breaking that into adding more cores, and then finally threads, multiple threads. And these are cores that let a single core operate sequentially on a couple of instructions streams, and you do that really just to take advantage of the idle time that you're waiting for memory. And then finally, you try to get more parallelism with GPUs. So, and then I want to kind of close with the idea of paradigms that I opened up in the beginning, and we're on the, this is a slide that was now almost 10 years old. Jim Gray, who posited the fourth paradigm, but first paradigm being experimentation or empirical observations. Second being theory. The third that Ken Wilson coined when I was at NSF was that the computation was the third paradigm for computing. And then Jim Gray said, no, it's data structures or data science as the fourth paradigm, that you, once you do all of that, it's how do you get your performance? How do you intuit that, and you use databases to look at what all the data you've generated. You've generated so much data that there's no insight at this point. It's only a large amount of database, and so we need a computer to do the interpretation of all that, and that became the fourth paradigm. And by the way, at this point, we created a hell of an argument within computer science of saying, no, there's only computer. It has nothing to do with paradigms or science or anything, but we do computer science and forget paradigms, and we still maintain paradigms are the right way to think of that. These are paradigms for science. And then there's a book, beautiful book about the fourth paradigm that you can download and use. Even though it's a decade old at this point, that describes this fourth paradigm, and lots of examples of that, of the science that's coming out from a data point of view. And so sort of what's next? Is there another paradigm beyond data science? And it looks to me we're seeing town halls here being created that are looking at AI as and machine learning as a way of forming the intuition. Now, given the fact that we've got these exascale computers being built at this point, there is an equivalent exascale investment in software that's being run from Oak Ridge, and there are a number of different facets of that. There are a number of exascale apps, everything from from fusion to through weather and the like. And then they conclude some of the things that are concluded from that. These are the software's got to do all this, and so we've got this huge effort that's really redoing or remaking the core applications for exascale computing, because you need there is so much rethinking that has to go on. And then that's what they added on the left. And I looked at it on the right and I said, wait a minute, and because I ran a Nexus, looked for exascale computing about 10 years ago for the Department of Energy, and I found that, to me, the greatest fear on this was something called verification and validation. That is, if you're running, doing work in high performance computing, and I hope it's something that all of you are this week are going to think about a lot, and that is verification is, does the program kind of do what it's spec to do or should be doing relative to the science and the mathematics, and then even if that's calculating, giving the right answers relative to that, does that, can you validate that if you're doing something in the physical domain, that has anything to do with the physical world that you're simulating? And finally, I'll sort of close with a friend of mine, Doug Berger at Microsoft, and that is, and also this equally same feeling is Dave Patterson at who was at Berkeley and now is at Google and building machines for neural nets and machine learning, and these are all their views that in fact we're entering a new era of programming, of building these highly specialized chips that do that. And this is the chip that Google uses for their actually machine learning or natural language processing, and also for looking at recognition. So we're seeing a lot being done in image recognition at this point. And so this structure's got just a lot of different kinds of cores in it, all doing different size arithmetics, but nevertheless delivering, factors of 100 or more over any traditional architectures, including the GPU. And then on the other hand, Doug Berger at Microsoft believes that in fact FPGAs may very well be the way to do it, so that you essentially unroll the computation and you simply pipeline results through that. So we have two quite different approaches for architecture that's being followed today, in addition to the big machines that are being built. So I want to thank you, and that's what I've got to say about the future, and good luck in terms of your endeavors to mastering these wonderful computers that you're going to be seeing in your career. Thank you. Away.
Bob, you want to go ahead and take questions there?
I could.
Thought that the supercomputer centers started after the size division at NSF, and I was looking at your slide that they actually started before. Is that correct?
Size started after the centers. The centers program was being formed about that time. So size, I came there in 80.
You're off camera.
Okay.
Okay,
Oh yeah. Okay. Yeah. Size started. I came in '86, but the program had started, I think, '84 or so. And then the centers. I'm trying to think when when the contracts were let. But there was actually, we had several centers, particularly one at Minnesota, and then there were, I think, another one someplace, another one that we had rented computer time to get the program started, and then those programs were canceled once the centers came into existence.
I have one more question.
Okay.
Back in 1965, I forget which machine it was, it had 36-bit words mentioned, and it was before the days of having machines where the 8-bit byte was the standard. So having that multiple of 3 in there, I'm thinking, did that cause a lot of programming challenges working with that system?
Well, wait a minute. There was that. It was actually those are 30s. There was a before. Well, I'll say the 8-bit byte was 1964 because that's when IBM announced the 360 and said the world is going to be 8-bit bytes. But before that, people were using 6-bit bytes. So the world was 36 bits or 18 bits or 24 bits based on the 6-bit characters. So it was all based on a character. And in fact, IBM machine they had decimal machines also that were 6-bit characters.
Most of us have just grown up in a world of 8-bit bytes, and it's
Yeah.
just, I would say it just makes my head hurt trying to work with
Right.
with these 6-bit bytes. So thank you.
Oh yeah. Well, what would really make it hurt is that before the 6-bit characters, the telegraph, it all kind of evolved from the telegraph, which was a 5-bit character. So a thing called the Baudot code was 5 bits, and so you had a lot of sort of overstrikes and things that were done.
Great, thank you, Gordon. We don't have any more questions. Thank you again for the wonderful presentation.
Okay.
So we got a couple questions from the Institute participants, if you don't mind. A number of the participants are in different scientific domains. So, for example, one of the participants said, as a third-year computational chemistry graduate student, they would like your advice on what they really should be learning to be successful as a research chemist, or fill in your favorite domain.
Right. Actually, I think I would. Computational chemistry, by the way, is very lovely. And in fact, let me say that I found it so lovely that I had met the person whose name I kind of slipped my mind right now, but he was at Carnegie Mellon. I had met him, and I said, that guy's going to get a Nobel Prize. And so fax number 2 or 3 went to Carnegie Mellon on the basis that I thought he'd get a Nobel Prize, and he did. but on computational chemistry, it was like, well, this is so obvious, but gee, how do you? Who would have thought you could compute chemistry with? But to the person on doing computational chemistry, I almost think I would go off and on some of those wild areas, unfortunately, delve into the AI aspect of and see what that's going to offer with vast amount of computation there that would yield something will put you in a kind of unique space. I mean, I've been I love looking at what's been done by David E. Shaw and that group that build the computational chemistry calculation that does all the atomic interactions. So I mean that's an area, but that's now being used pretty constantly. I would think something that maybe an AI that where you have essentially you get more chemistry done for computation. But I think, I mean, that's one way you can head, and that would be to sort of go into a lead and field and lead part of the field there.
Very good. Another question. A participant said, great talk. I understand the upcoming trend of using FPGA for spatial computing geared towards data-intensive science. How might that affect the scientific algorithms? Can we expect to transfer knowledge from temporal computing, or do we need a new and fresh perspective?
I don't know. I think once you start down that path, because you, in a sense, in a way, the FPGA gives you almost a new, or it requires a new perspective. I mean, the simplest form is the whole computation is unrolled, and you simply everything is now pipelined, or the computation is, or the algorithm is mapped into to a single physical or planar or I'm sorry, into a something, you know, that's it's I guess to a hardware guy, I kind of see FPGAs is now everybody is kind of has to go back, and you end up having to think about things a lot differently, because we were using, when we worked actually now 30 years ago, built a thing called a graphics supercomputer, which was actually a 4-processor Cray architecture with graphics in it, and all of that was done with Verilog. So what you're doing with FPGAs, you'll be programming in Verilog, and so I get. By the way, to the previous question, person looking at an avenue, you might actually look at Verilog as your computational paradigm, as a way of shifting out of the normal sequential thinking that you would normally do. Verilog is going to be done, everything's going to be running in parallel. So Verilog might be a good place for everybody to start if they want to, particularly if they want to use FPGAs. And right now I would advocate FPGAs versus waiting for somebody to hand you a new chip that you have to program. So you go program your own, whatever you want. And we're finding that works very well in data centers, particularly things the data centers being a different, or the cloud being a different kind of computation, but nevertheless, FPGAs are the approach that Microsoft is using. Virtually all the machines there in the cloud have front-end FPGAs in the front end for various reasons.
Very good. And one final question. Do you have any projections or expectations of what we might expect from quantum computing?
Right. My favorite quantum computing. I'm too old to even think about. I don't know. I mean, it's, you know, I generally use a 10-year rule or 11-year. Actually, Carver Mead told me it's 11 years. And that is from the time something appears in a laboratory to the time you can actually perhaps buy one or two. It takes 11 years. And so until we kind of see some problem, important problem being solved in the laboratory, yeah, you can't really turn the clock on. So I have no expectation for a while. And everything I read tends to be follow my, the rule I had was, gee, I'm going to be out of business before it gets into business.
Okay, well, that's it for the questions. I want to thank you again very much for the fantastic keynote presentation, and many thanks to Bob and the San Diego team for hosting you.